So my name's Matt, and we're going to be talking about fluid dynamics in Notch. This is going to be a really technical session. I'm not going to lie. This is going to be a really technical session. You can treat this session in one of three levels. You can either treat it as a way of learning in depth how fluid solvers work in computer graphics, or you can take it as a list of things to go away and Google, or you can treat it as just look at the high level of how you set stuff up in Notch. But it's going to be quite heavy. Sorry. So what is a fluid? I Googled. A fluid is, according to Wikipedia, is a substance of no fixed shape that flows and deforms freely, yields to external pressure, and it's generally incompressible or compressible. Gases are compressible, meaning you can squash them and they fit in a smaller space. Liquids are incompressible, meaning if you squash them, they burst out, but you can't squeeze them into a smaller volume. And fluid solvers in computer graphics have been around for quite a long time. They come in sort of two major forms. First is Lagrangian methods, which basically means you model the fluid as particles, lots of particles. So particles flow around through space, and when they interact with each other, they spread their forces and so on between each other, and that makes them behave like a fluid. And in Notch, we have a couple of those. The SPH node in Notch is a particle-based fluid solver. And the second type is Eulerian methods. And this means you have a big grid, and in each cell of the grid, you say how much fluid there is and how fast it's moving and so on. So if you want to add more fluid, you just say to each cell you've got more in it. But if you want to move it around, it's quite complicated because you have to move stuff between grid cells. With particles, it's very hard to add more fluid because you have to add more particles, but it's very easy to move them around. So inevitably, there are loads of big commercial fluid solvers out there, and they either do one or both of these things, and both have their strengths and weaknesses, and we'll talk about what those are. Eulerian methods are fields in Notch. So fields are a Eulerian fluid solver, basically. And then there's some hybrid or semi-Lagrangian methods, which use a bit of both. So they use particles to model the fluid, and they use the grid to push them around. One important thing to note is that all fluid solvers are simulations, which means that frame rate has a major effect. They're not animations. If you change the frame rate of the simulation, it changes quite a lot. So if you want to have a reliable simulation that looks the same every time, you have to lock your frame rate. Particularly if you're doing something in Notch and then you want to render it out to a video, and you are simulating at 60 in Notch, or sort of 50 or 60 or whatever, and then you render it at 30, it's going to look different. So you need to lock your frame rate in Notch to make it look consistent. So I'm going to start by talking about Eulerian fluids fields, in particular. So a field, when you're modeling fluids as a field, you have a fixed resolution grid, and each cell stores how much is in there. And solving moves fluid from cell to cell, which is generally called advection. In particular with fields, when you add a fluid effector to the graph, this does the job of actually simulating pressure. So without the fluid solver, stuff will flow from cell to cell, but it just looks kind of noisy and turbulent. It doesn't really look like a fluid. When you add the fluid effector into the graph, it starts solving pressure, so you get something that actually acts like a fluid. So on the field root node, there's some options. One of the options is the mode that it generally uses. And in general with fields, you get colors and you get velocities. So you can inject color and you see it in the graph. There's a mode in the field root node called densities and temperatures. And this makes it act like a proper fluid simulation. And if I just do a really simple setup here. So here's my node graph for this setup. So I just have a small ball of emitting in the bottom of the field, and I stick a fluid effector in there. then this is what's going to happen when I run the simulation. So the ball is emitted with some density and some temperature. It's got a temperature. And the temperature makes it have an updraft. So because it's hot, it heats up, it pushes up the fluid. But as it goes up, it cools. So as the fluid ages, it has less temperature, and it means it moves up less quickly. And but the effect of pressure, when you add them all together, it gives you this kind of mushroom cloud look. And this is like, I imagine everyone has seen this like 100 times with various like fume effects and all the other solvers out there. This is a very basic fluid look. So if you set this up in Notch with just the few nodes, you don't even need the turbulence effector there, and you hit run and you have the right parameters, this is what you'll get. So we're going to go through now when to use this and why, and how to make it actually look decent, and some of the common errors that people introduce. So pros and cons of using fields to solve fluids. So the pros are that it's a grid. So it's really easy to fill and make it dense because you just add more stuff into the mix. But the biggest con is that it's a grid. So the area covered and the resolution is really limited. If you want to make a field look more detailed, you've got to increase the resolution. If you want to make it bigger, you've got to increase the resolution. And either way, is you either make it bigger and it gets less detailed, or you make it more detailed and you need to make it smaller. But if you want to do both, you've got to increase the resolution. And if you want to increase a field from 256 cubed to 512 cubed to double its area, it makes it 8 times slower. So this becomes a major problem. And balancing these things becomes the critical thing about this whole issue. So the pros and cons continued. It's easy to make a fluid like with fields feel continuous, like you don't have little gaps and holes. It feels like one solid thing in space. And the simulation's pretty stable. But collisions are pretty difficult. It's hard to make collisions behave in a good way. And the whole nature of the way this is solved, you naturally lose detail and it naturally blurs out over time. So this is one of the other big problems. It's stable, but it loses detail. And with gases, it's not really that massive a problem, but for liquids, it's a really big problem, which we'll come to later. So naturally, you hit run and you have something that starts off detailed and it gets more blurry. So now I'm going to talk about how to make these things look more detailed and more good. The first thing to take care of is resolution. So a field has a bounding box, as you're probably aware, and it has a number of cells, like a width, height, and depth. And what you need to do is you need to make your bounding box as tight as possible around the thing you're trying to solve, the area you need to solve. And then you need to take the resolution settings and balance them so they make sense with the bounding box. So for example, if you've got a 1080p screen and you're trying to fill it with a field, then your field should probably be around 16:9 in aspect, and the number of cells should be about the same. So if you're trying to stretch a field to fit a screen, then the width and height should be different. The number of cells in X and Y should be different. You should have more cells in X, so your cells are approximately square. So think about each axis separately, particularly the one going into screen, because often the direction you're looking down is the one where you can get rid of most detail and get away with it. It's the sort of viewport X and Y where you need a lot of detail. There's an option in the root node, a field root node called upres density field. And what this does, there's two parameters in a field. There's the velocity that each cell is moving at, and there's the density. And it's the velocity that's really slow to solve. This is where you actually have to do, this is the one you operate on to solve pressure. And density is the one that actually makes it look detailed. So there's an option in there to make the density twice as high res as the velocity. It means that you get a reasonably fast simulation, but you get a lot more detail. So that can be a very useful option. The next thing to add detail, the fluid effector node has a parameter called number of iterations. The higher this parameter, the slower it gets and the more accurate it gets. So because we're real time, we don't do a fully accurate simulation. We try and cheat as much as possible and cut corners as much as possible. If you want your simulation to look increasingly accurate, you increase the number of iterations. And you can also add turbulence, so you can cheat and just use a turbulence effector to add a little bit of noise to compensate for when you're losing detail and it's blurring out. And then you've got this parameter called vorticity confinement, which we'll demonstrate in a minute. So this screenshot shows the left and right image are exactly the same simulation. The difference is that on the left image, the bounding box is way too big. So exactly the same resolution, same simulation, but the bounding box is stretched. And you can see what happens. Like just by getting that wrong, I've got a really blurry, no detail simulation. If you're seeing that with your fields, it means that you need to make things smaller or increase the resolution. So next is this magic parameter called vorticity confinement on the field effector. So what vorticity confinement does is it adds little swirls of vortices as the simulation develops, where the simulation's moving quickly, to try and add back in the detail that's lost. And you can see the effect left and right, like the original solve versus the one with vorticity confinement ramped up. And you can see how what a major effect that has on the detail of the simulation. Finally, adding turbulence. So adding turbulence changes the simulation, but it can make it look more interesting. And you can see there's an awful lot more detail just by a little fine turbulence being injected constantly. So collisions. I said collisions were an issue. So the way you have to handle collisions when you're talking about a grid is you have a solid object that's you have a solid filled object that's your collision object. And inside the object, you just delete all the fluid. And on the boundary of the object, you try and do a solve that makes the pressure on either side level out to zero. And this is quite not entirely trivial. So it often doesn't look quite as great as you might hope. And you can get a loss of volume by doing collisions, which again, for gases, not much of an issue. For liquids, big issue. You can see the effect here. I've got a solve with a sphere. And you can see the thing wraps around the sphere reasonably well. So that's using a primitive collision effector on the field. So a quick word about shading. So I'm using temperature and density mode on the field root node. So this doesn't map. This is not a color. So you can't just render it. You have to do something to it to make it rendered. Density maps really obviously to opacity. So you just use the density as the alpha channel. Temperature is what you turn into a color. And that we basically take the temperature, we map it to a color spectrum gradient, or in fluid terms, or in the field terms, we let you specify a color. And if you see here's what the different elements are. So density just maps to opacity. And if you use density and you light it, you get this kind of nice shadowed look. And then we colorize the temperature with just an orange and a gradient. And then we combine the two together and we get quite a decent fluid look. And there are examples of this now in the 921 release, so you can go and try this out. I think Armin even put one on the user group at some point. So that's gases through a field solver. Now we get on to level sets, which was added in 0921. Boys, is anyone familiar with level sets at all? Is anyone coming from like Houdini or anything like that? Not bent. You're not familiar with anything. So what is a level set? In sort of solver terminology, it's a lot like the field solver, but instead of storing the amount of fluid in each cell, you store the distance to the free surface. So if you think about my bottle of water here, The free surface is, unfortunately the label's in the way, but the free surface is the line where the water surface meets the air surface. And each cell of the fluid stores the distance to that point, to the closest to that point. And solving works pretty much like the field effector. But what you're doing is you're constantly updating that distance to the point where the water meets the air. Otherwise, it kind of works pretty similarly as the field solver, with a couple of major differences. One of them is, so in a gas, the point where the gas meets the air, they're kind of the same density, more or less. So they exhibit about the same amount of pressure on each other. The point where water meets the air, water exhibits a lot more pressure on the air than the air does on the water. So you need to change the simulation. So for this, we kind of only consider the pressure of the water on the air. And we generate so we do a pretty much similar solver otherwise, but we only apply gravity and external forces to the area inside the surface, not outside. And we have to fix up the distances every frame with and there's an iteration count on the level set root node, which says how much to fix up the surface every frame. The more you do it, the more accurate it gets and the slower it gets. Do you see the theme here? Because it is constant with this. And then to render it, we put it into a procedural system to render it as a mesh. And here is, so here's something I rendered out with level set. So I made a ball, just emitted from a ball, and that just drops to gravity. And you can see as it falls, it just time evolves and it hits the ground. By the end, it hits the ground and forms into this kind of splat. So it kind of looks believably like it's acting like a fluid. So this is where incompressibility becomes an issue. So the way you solve pressure with Eulerian fluids is you do what is called an iterative solver. So you're trying to accurately work out how much pressure each cell is exerting on the ones around it. And to do this, you have to do this operation. It's basically like smoothing out the pressure field over time. And this is done iteratively. So it's a bit like a massive blur. It's a bit like the blur node, right, in Notch. So the more iterations, the more blurry it gets. But in this case, the more iterations, the more accurate and smooth it gets. So you can vary it. You can make it less accurate, but faster, or you can make it more accurate and better looking, but slower. With gases, which are compressible, it doesn't really matter if it's not completely accurate. With liquids, which are incompressible, if you get it wrong, it basically means that it's going to be compressible. It's not going to hold its volume. So if it's not fully solved, you're going to lose fluid. It's going to leak out. So when you drop the ball on the bottom of the volume, it's just going to disappear out the bottom of the volume. It's a bit of a shame. So there's kind of two ways to solve this. One is you do so many iterations of the solver that it makes it completely right. And then you're sort of in seconds per frame territory. Or you cheat. And the way you can cheat is there's an option in the field level set node to pump a little bit more fluid in the bottom every frame. And that gives you the appearance of it not leaking out. And this sounds like a really horrible thing to do and a horrendous cheat. And so many solvers do this, not just in Notch, because it's actually a decent way of getting around the problem. So now I'm going to go on to particle-based methods. So particle fluids, logically, the fluid is stored in particles. And each particle just stores how much it's moving, how dense it is, and so on. And if you have lots of particles together and they're all moving coherently, then you get something that looks like a fluid, not just a few particles moving randomly together. And as they move around, obviously the fluid moves. But obviously particles have to affect each other. They have to exhibit a force on each other, so they can't get too close. They also have to try and keep together so they don't get too far apart. And their velocity has to be smoothed. If you have one particle moving really fast and it approaches a bunch that are not moving, The aggregate effect should be that they're all moving a bit, not that one's moving really fast, because that doesn't look like fluid. So you have to do this operation of smoothing the particle's motion and density across its neighbors. And the SPH node in Notch, the SPH particle effector node in Notch, does exactly this. So this stands for Smooth Particle Hydrodynamics, which is, I think it's like an astro kind of term, astro fluids. But basically what it means is particles apply forces on each other and push each other apart, and they also pull each other together to try and form a coherent whole. And they smooth their properties their velocity between each other. So here's the SPH properties. There's only a few which are really important. So to help you understand how to get a good-looking fluid, I'm going to explain the 3 key parameters to using this node. So there's 3 key parameters. The first one is cell size. And what this basically means is how far apart the particles affect each other. And you need to set this based on 2 things. If you have a very large unit scale, then you need to make the number bigger. And if you've got a very small unit scale, you need to make it smaller. So the fluid acts as it should to the scale of your scene. The other thing you need to consider is the amount of particles you have. If you start with, say, 10K particles, and you want to change that to 50K, but have the fluid take the same area, you need to reduce the cell size accordingly so the particles don't push each other out as much. Otherwise, it's just going to get bigger. The second parameter is viscosity, which is basically how much the velocities of the particles smooth between their neighbors. So if you have a very low or 0 value of viscosity, you get something that's very gassy and noisy. And if you have a very large value of viscosity, you get something that's more like treacle or wax or something like that. So the bigger values, the more it's smoothed. And if you're going for like a decent looking liquid, you probably end up with values in the sort of 10 range. And the final parameter is surface tension, which is how much the particles try to stay together to form like blobs and balls and so on. So if you have small values, they don't form and they just act quite gassily. And with large values, they pull together to form drops. And then you've got a bunch of other parameters on the node, things like dampening and rest density and pressure scale and so on. And they're all there to help you make a simulation that doesn't blow up. SPH is prone to exploding. So if you have small variations in frame rate, some unfortunate particle positions and so on can cause a small thing to become a very big explosion of particles that doesn't look like anything anymore. So with these parameters, you can dampen the simulation or limit the amount particles can push each other apart to try and stop the simulation exploding. So here's a similar example to the level sets, emitting a ball of particles and dropping it. And you can see the rough kind of form is similar. Ball drops, hits the floor, exhibits this kind of fluid crown-like shape, and then expands out. And if we go to the next slide, you can see how it expands out. So as it settles, it forms into a kind of flat area over time. So pros and cons of SPH. It's easy to cover a varying area because you're not limited to a grid. Particles can go anywhere, and so a fluid that has to move around a large area is easily modeled with particles. However, to make it dense, you need lots and lots of particles, which makes it slower and slower. One of the greatest strengths of particle SPH solvers is that it's quite easy to do accurate collisions. It's really obvious to think how to make a particle collide with a wall, because it's just one particle. And because the particles can push each other apart naturally, and because collisions work well, it's easy to make a simulation that holds its mass, holds its volume, and doesn't leak out. Like, it's very easy to make particles constrained to a box and not leak out. You just have to make them collide with the box properly. And that's a really useful and important property. But they are, as I said, prone to blowing up, particularly with variations, little variations in frame rate, or by having them just emitted way too close together in the first place. So let's have a look at collisions. So here I've got a ball of a collision ball, and the particles are bouncing around inside the ball. And you can see that it all behaves really well, and they maintain that they don't leak out of the ball. So it works well. And you can use this with, you can use collisions with solid objects comfortably. You can use 3D meshes as long as they're closed and solid. You can easily make a fluid that flows inside or around a 3D shape. So the last big method is called flip. Is anyone a Houdini user here? Yeah, there might be some people who are familiar with the flip solver in Houdini. And we have one too. So flip is fluid in particle, it stands for. It's actually two modes. There's fluid in particle, flip, and there's particle in cell, pick. And this is done with the fluid flip effector in Notch in the particle system. And what this does is it uses a hybrid between grid-based and particle-based solutions. So the fluid's modeled as particles, and you give it velocity with particle effectors, and you collide it as particles and so on. But when you want to solve the fluid element, you splat all the particles into a 3D grid. And then you do all the pressure solving exactly as you did for the fields. So it's a hybrid between fields and particles. But at the end of the frame, when the solver's done, you chuck the grid away. So there's no grid to worry about in terms of stuff moving around. The grid's a really good way of solving pressure in a way that looks nice. So when you see the splat, you can see that you get something that looks quite detailed, it's quite splat-like, I guess. And it has a lot of detail, but you can do this without a very high-resolution grid at all. So to achieve this kind of detail with a proper, like a level set solver, you'd need a really big grid, and it would be really heavy. To do it with a flip solver, you can do it with a really small grid, like 64 or 1/8 cubes, so it's fast. It's fast and efficient. So that's the thing. So unlike fields, the particles, you don't lose detail, you don't have issues with collisions, and you don't need a very high-res grid, on the other hand. It's stable. It's limited area, though. You have to give it a bounding box around the simulation that says where the grid goes, basically. So there is a limited area issue. And as well, because you're solving on a grid, you have these you have these pressure and losing volume issues, exactly like level sets. So you can see in my splat, this does not fill out to fill the box. This leaks out the bottom of the box because the pressure simulation isn't good enough to keep the particles apart. So all that happens is that shrinks away to nothing. Not ideal. So if only there was a way to combine the sort of nice-looking simulation of flip with the stability of SPH and the sort of volume conserving of SPH. Unfortunately, there is. You can use the flip SPH solver. So the flip SPH solver, so in various people have done this in other, like in Houdini and so on, and they've actually made a solver that combines flip and SPH. In Notch, you just have a SPH node and a flip node, and they both work together and it's fine. So this is a real best of both worlds solution. So the SPH keeps the particles apart and means that they retain volume, they don't leak out. It enables it to fill out to a solid area. But the flip solver gives you detail in your velocity solve and your pressure solve. So it makes it look much more like fluid waves and not like a gentle drop in the ocean. So here's some shots of the flip SPH solver in work. So you can see that as it drops down, I didn't include the very first shots, but as it drops down, it forms, it fills out the box really well without leaking out, and it settles and flows out nicely, but with a lot more detail than SPH had alone. So I've got side-by-side comparisons. I Identical simulation with SPH, but with the one on the right also has the flip solver, and the one on the left just has SPH. And you can see straight away from the first shot that the one on the right looks way more like fluid than the one on the left. And as that evolves, you see the SPH one rapidly settles into something quite boring, and the flip SPH maintains like a nice wavy kind of watery look. And that continues to go through as it settles. And there you go at the end. So this gives you a really nice combination of techniques. So the final thing to talk about is surface reconstruction. So what do you do if you have a load of particles and you want to make them actually look like a fluid and not a load of particles? So the way to do this in Notch is you have a procedural root node and a procedural particle node and a procedural meshing renderer. And you can turn the particles into a mesh like you would do in RealFlow or anything else, very similar, or OpenVDB. It's very similar to OpenVDB's mesher. So we do surface reconstruction with that. But the particles are modeled as basically modeled as blobs and brought together and meshed. So the challenge is how you make something look like not just a collection of blobs or spheres, but actually like a continuous shape. So if you look at the surface reconstruction here, as the ball falls and as it settles, this is working reasonably well. So the major thing to be aware of so when you set this up, first the big gotcha that always catches everybody is the procedural meshing node and the procedural particle node have their own bounding boxes and they can be set differently. If you want to make this work in the way that you expect, you have to link the bounding box to both nodes. But otherwise, it's going to be weird. So the procedural particles node naturally generates spheres. So you need to balance the size of the sphere and the smoothness. And you can smooth the meshing node afterwards. So the way that most meshes work is you generate a rough kind of blobby thing with the particles basically, and then you do a ton of smoothing on the mesh to make it look more fluid-like. We've got some shots of how this affects the mesh. So the mesh on the left has been smoothed, and the mesh to the right has been made as blobs. And you can see this, if you can see the screen in the sunlight, you can see that there's quite a big difference. Like one looks like a bunch of spheres, and one actually starts to look more like a fluid. And then varying the particle size. So if you increase the particle size, then it gets more blobby. But if you decrease it, you end up with holes in the mesh. So you have to balance getting it looking detailed and getting it actually looking solid and smooth is a balancing act. Okay, that was very deep. Rather than talking more, I'm going to ask if anyone's got any questions. Yeah?
Do you have an example of the node layout? You were saying it's a procedural node, and then how to get the surface from the part.
I think there is some in the samples, actually, already. Yeah, there should be a procedural particle sample in.
I saw the procedurals, but I couldn't find out how to turn particles and positions into the surface, the last thing.
Yeah, there's a procedural particle. Particle generator. It's in the procedurals generator section called particles.
Okay.
What was that, Armin? Yeah, Armin is going to cover this, so I don't have to. And as another aside as well, like if you're doing, you can use Notch. Something Ryan's going to cover in his talk later today is using Notch to simulate particles and then bake them out to like a lembic cache that you can load into another system to do the meshing, or doing a particle system in another system and then baking that out to a lembic cache and loading that into Notch for meshing. So you can go both ways now. Yeah.
Can you just say bounding box for both of them?
Yeah, there's a bounding box input on both nodes. So yeah, and that probably goes for like, because the flip node's got a bounding box, everything's got a bounding box. Use one bounding box, link them to. For the procedural meshing node and the procedural particles node, they both have bounding box inputs.
If I use the bounding box in the root, it won't bound all what's connected to the root?
It actually might. Armin, can you remember if it does?
I would love to answer if my
If you connect the bounding box to the root procedural root, does it apply to both? I think it might. Yeah, it could. Yeah, that might work. Yeah.
Is there any secondary particle emission, like for example, UFO has hydrogen?
Like splashing. You could probably do it with particle events on collision, and you can probably do it with particle events based on velocity. So, have you tried particle events? So, if you could probably make it that if the particle is moving fast, it emits new ones. That might work. It's not exactly the same, though. It would be interesting to try them.
Do you have any tips or anything to help with collisions with other elements other than self-collision?
Yeah, like meshes and so on. Yes. There's several collision effectors in Notch. And this is something I'm going to cover in the physics talk tomorrow afternoon, actually, but in more detail. But generally, some things are really good colliders, and they're really solid and easy to make work. Like primitives are really easy to make work because they're completely solid. So there's a primitive collision effector, and if you want to collide with a box or a sphere, you should use that because it treats it as a volume. So if particles go inside it, it knows how to push them out. If you use the straight collision effector with a mesh, it treats them as it's the thin cells, it's thin like sheets. So particles can get through. If you can use procedurals as collisions, I believe, and they're also solid. Some of this stuff is probably only going to be in 922, but you can, yeah. So firstly, using a higher frame rate as possible. So you can lock the frame rate of the particle sim, and you can lock your overall frame rate. So if you go for a higher frame rate, particles will move less fast, so they won't step through. And you can also increase the radius of the particles. And it's also like silly tricks, like if you have a bumpy, if you have a mesh for a ground plane, put a primitive plane underneath it just to make sure that you can double up colliders. Like if you really don't want stuff to get through, you can use a simpler shape underneath a complex shape.
Can we cache the particles? Like if it is more than 2 billion particles?
We have in 922 that you can bake out particle simulations, yes. But bear in mind that if you're doing a 2 million particle bake, there's going to be like a gig of frame or something. So it's going to be really, really, really big and really unwieldy. But you can do it.
Is there a way to affect geometry velocities into fluids?
I think if you use an object emitter, it should give the velocity. It should input the velocity into the field. It should push the velocity in, and then you use the field effect, and it will spread out because it'll only do it in the cells where the object is. It won't do it around it. You have to use the fluid effector to get that to spread out. It should work. Yeah.
Sorry. What about the emitter having that be a collision effect? So if it was some model that has, like, say something before, like it's an L-shaped emitter, and some of the particles emitting it, like some of the models, like one of the examples I have, it passes through the generator. What would be a way to set that up, or is that being tweaked, or you know what I'm asking?
Yeah, you'd need to not emit the particles inside the shape, unless you could probably do it by. You might be able to do it by making collisions single-sided, and then if you emit inside the shape, they should be able to escape from the shape on the first bounce, and then they'll hit the shape when they try to go back inside it. That's a bit tenuous, though. The other way is probably, so if you're doing with particles, so one thing to be aware of with particles is that you can mask effectors. So a collision effector only affects a certain set of particles. So you could, for example, break off the bottom of the L and have only that affecting the particles that emit in the L, or emit outside the mesh to be safe.
Standalone generator, not necessarily both.
Yeah, you probably need to start getting smart with like separating the collider and the particle mesh.
Just, the best way to do water would be to use the particle system, either the procedural or the SDH.
Probably, yeah. That's probably the best way.
Gas things like fuels.
I would use fields for gas, exactly. Yeah, definitely. I think we're all done. We're all done. Thank you very much.